Okay, I think that means we're live. So, good evening, everyone who's joining us. We're really excited to welcome you for our next public lecture. And today we're joined by Professor Sharf from McGill's Department of Mechanical Engineering. You're welcome to ask questions anytime in the various stream chats throughout this talk, and we'll have a couple pauses, I think, where Professor Sharf will be able to answer questions as well as at the end. And so we're going to today hear about Professor Sharf's super exciting research on space debris capture and removal. And so with that, please take it away.
Okay, well, thank you very much for the introduction. Good evening, everyone. Thank you very much for inviting me to give this talk. I'm really happy to have this opportunity to tell you a bit about our research, and I want to thank everyone for joining in. So the first thing that I would like to do is actually acknowledge the work of the people in my research group who are really behind this work, and that's my amazing PhD students, Eleonora, Mikkel, Catherine, Tai Chow, Luke, Mikhail, and Pamela Wu, who was a research associate with me, and also a longtime colleague and collaborator, Professor Luna Misra from my department. So here's the overview of my presentation. I'm going to first give you some general background on space debris, and also introduce you to the concept of space debris removal and why we are looking at this problem. And then I'm going to focus on some of our work with a little bit of sprinkling of work of others. And I'll talk about active removal of large debris. I'll talk about mission for multiple debris removal. Then I'll talk about passive debris removal. And I'll end with sort of some of the more scientific aspects of our work related to understanding and predicting rotational motion of debris. All right, so a little bit of background. So what is in near Earth space? And for the most part, our work is confined to things in what we call the low Earth orbit, or LEO. So as many of you know, in the last 60-some years, we've been launching things into space, and we've launched more than 10,000 satellites, and most of them are still in orbit, but most of them are also not functional anymore. So approximately 2,300 are still operational systems. These numbers are a little rough, and of course, they're changing continuously. Around 34,000 objects are larger than 10 centimeters in size. And I specifically mention this because these objects are trackable from the ground, so we can track them from instruments on Earth. And then we have something on the order of 1 trillion objects of size that's smaller than 5 centimeters. So what is space debris? Well, the space debris are comprised of things like, obviously, defunct satellites, so satellites we launched that are no longer operational, and upper stages. Upper stages are parts of rockets that are helpful for launching satellites, as shown in this picture that I have. Then we have things that are fragments from collisions. And these collisions can be collisions between satellites. For example, we had an accidental collision in 2009 between Iridium-33 and Cosmos 2251. And then sometimes we have intended collisions, as was the case with an anti-satellite test conducted by China in 2007, where they destroyed their own defunct satellite, Fengyan 1C. And then we have things that are fragments from explosions, as, for example, a battery explosion that happened on the NOAA-16 satellite in 2015. So all of these things contribute to space debris of all sizes. So why space debris problem? Why are we sort of concerned about this? Well, of course, space debris create increased space debris pollution. And what happens is, as objects collide in space, they will generate an increasing number of additional objects, and as those collide, and there's more debris, and this is what's called Kessler syndrome, named by Kessler in 1978. And so essentially you have this sort of exponential like growth of debris. And from a practical perspective, this creates a collision threat to operational spacecraft. And even an object as small as 1 centimeter in size can create substantial damage. Why? Because of relative speeds that things travel at in space. For example, speeds as high as 10 to 20 kilometers per second in LEO. So even a small object traveling at that kind of speed can pretty much take out a functional spacecraft. Now, so you take all of this in the context of where we are now, and we are now in the era of mega constellations. We have companies like SpaceX and OneWeb and others launching thousands of new satellites over the next decade. So you can see how this is becoming a concern. And so that brings me to the topic of active debris removal, or ADR. So currently, there's really general agreement on the need for active debris removal. And the big focus right now is on removing large debris. So these are objects that have the greatest probability of generating the highest amount of fragments in the future. So they tend to be massive objects like defunct satellites and spent rocket bodies like the upper stages that I was showing earlier. And there is currently sort of a consensus among researchers in this area that removal of 5 to 10 large objects from LEO, from the low Earth orbit, per year should stabilize the growth of space debris. So this is based on predictive models that we have for debris growth. All right, so we sort of think that we need to do active debris removal, and we think that we need to remove the larger, more massive objects first. And large space debris are difficult. So first of all, as I said, this is by definition, they tend to be pretty massive, which means that removing them gets to be expensive. So as an example of a debris, I have a picture on the right of Envisat, and this is sort of, in my group, we call it the most desirable, the most sought after debris out there. So this is a spacecraft that's about 8 tons in mass, and it's the size of a school bus. And as you can see from this picture as well, many of these large space debris have complex geometries. They're made up of multiple segments. So you have the bus of the satellite, then you have the solar array, which is sort of off to the side, and then you have a large antenna as well. And that creates problems when you're trying to grab or capture one of these objects. Another issue is that these things tend to be tumbling because they're usually no longer under attitude control. And so they're sort of rotating in this, kind of not very clear fashion. You can't identify a fixed spin axis of rotation, and they're literally tumbling. And another thing that makes it difficult is that they don't have special grapple fixtures. They don't have handles by which you could grab them when you're trying to capture them. So all of these sort of characteristics make large space debris difficult. So what would a typical active debris removal mission look like? Well, basically, you need to launch a removal spacecraft. And in this field, we usually call it chaser, the chaser spacecraft. Then that spacecraft has to rendezvous with the target debris. It might need to analyze the motion of the target debris, and then it's going to capture it in some way, stabilize sort of the whole system, depending on how the debris was captured. And then the whole system is deorbited with the chaser spacecraft, essentially firing engines to bring the whole system to Earth. So one of the things about ADR is that it's complex. It's a multi-stage process. There are many sort of elements in these missions. It's multifaceted, and to date, we have not had a real mission where a real debris has been removed. But we have had some demonstration missions, and I'll mention here specifically the Remove Debris mission that took place 2-3 years ago out of the University of Surrey. And currently there is a mission going on, which is called ELSA-D. And this mission was put up by Astroscale, which is a Japanese startup. So let me now say a few words about our research on ADR. And in my work and the work of my group, we've really focused on one of the parts of the mission, which is related to debris capture. And we've investigated two approaches for capture. One is what we call a robotic capture, and that's where the chaser, I'm not sure if you can see my mouse, but the chaser is equipped with a robotic arm, as shown in this picture, and the robotic arm literally grabs the debris to capture it. And the other is what we refer to as tethered net capture, and that's illustrated in this picture. And that's where we throw a tethered net towards the debris, and the net envelops the debris, and then we tug the debris to deorbit it. And I'm going to say a bit more about both of these approaches. So starting with the robotic capture of space debris. So again, sort of the idea here is you have a servicer, they chase a satellite. It's equipped with a robotic arm, as what's shown in this picture. This is a 7-degree freedom manipulator. And you are using the robotic arm to capture the space debris. So this in itself is also a multi-phase operation, and then includes things like approaching the debris, because you need to get close if you are going to grab it with the robotic arm, the actual sort of grabbing maneuver. Then if the debris, given that the debris is tumbling and you had to be moving the robotic arm to grab it, you need to sort of rigidize the whole system. And then you want to berth the chaser to the target to make them a single sort of body that you can then launch towards Earth. So for a number of years, we carried out work on sort of the approach and grabbing aspects of this by using a facility that I had in the lab, in the Aerospace Mechatronics lab. This is my lab here at McGill that I co-direct with Professor Meir Nahon. And we used the blimp, which you see here in red, to emulate a debris in space, right? Because the blimp is free floating, and then we had a robotic arm, and the robotic arm would essentially go towards the blimp and then try to grab it, as it just did here. And I'll show you here another video of the setup. We have another version of the blimp here in white, but it's basically the same idea. The robotic arm moves towards the blimp, grabs it by a little handle, and tries to sort of stabilize. Another thing that we did on the robotic capture was we worked on post-capture specifically of Envisat satellite. And this was done as part of a contract that I worked on with Professor Misra a few years ago, and this was a contract with Airbus DS. And so the two aspects that we worked on here was actually the immediate post-capture, where you want to rigidize the system and then berth the servicer to the target. And so this was really specifically oriented towards capturing Envisat. And again, just to remind you, it's an 8-ton spacecraft, very large in size. It was declared to be a debris in 2012, and it's tracked by observatories worldwide, which will be relevant to the later part of my talk. So in this work, we used the dynamic simulation to basically study the system rigidization. That's after you've captured Envisat, which is tumbling, and you're trying to make the whole system rigid. And then you want to use the robotic arm to bring the chaser, which is this kind of goldenish body, to berth, to dock to the launch adapter of Envisat, because once they're docked together and they're firmly sort of put together, then you can fire the thrusters on the chaser and launch the whole system towards Earth. So this is a movie. You see 4 panels. It's the same thing, just sort of 4 different views. Again, this was done with the dynamic simulator. And what you're going to see here is the berthing of the chaser to the launch adapter of Envisat. And the things to sort of maybe appreciate here is that you have to do this without colliding, having anything collide. You don't want any collisions of the robotic arm with any parts of the debris. You don't want the chaser to collide with anything, right? You want this done smoothly. It has to be done accurately. Airbus at the time also gave us time constraints on this particular maneuver. They wanted it done, I believe, within about a minute. And all of this has to be done, of course, within the constraints of the actuators of the robotic arm. So that was a really fun project, and we got to go to Germany to present it to Airbus at the time, and it was really an exciting project to participate in. All right, so now I'll talk about the net capture of space debris. So this is our second approach that we investigated in my group. And this approach was and is still considered a very sort of strong contender to the robotic capture for several reasons, and it has a number of benefits. For one, it's a very scalable approach. If you make a large enough net, then you can capture the debris of several different sizes. Another kind of nice feature about it is that you don't have, there's no collision risk between the chaser and the debris target during the capture, because you can actually maintain a pretty substantial distance, like 50 meters, between the chaser and the target, since you're launching the net towards the debris. And this is very different from what we saw in the robotic capture, where the chaser has to be pretty close to the debris, which of course, makes it more difficult. And another benefit of the net capture is that it's better for capture of tumbling debris. So even if the debris is tumbling, you don't sort of need to worry about it so much, because you're just kind of throwing literally a fishing net over it. And the fact that it's tumbling is not so much a concern. So how does this work? Well, basically, you initially have the net in a canister on the chaser, and then the net gets ejected out of this canister with corner masses. So at the corners of the net, you have kind of masses which get ejected through some sort of a mechanism, and those masses then sort of pull the net with them. And you entangle the debris, sort of contain the debris inside the net, and then you tug this sort of system to the disposal orbit with your chaser. So that's the basic idea. Now, as with anything we do in space, we want to be able to have simulation tools, reliable simulation tools, so that we can use them to plan the mission, to do the analysis, to investigate our different options, see how different parameters of the system might affect the success of the mission. And so when we started to work on the tethered net capture, there was actually little prior work on dynamics modeling and simulation of these systems. And so we embarked on developing such models and tools. And I thought I'd show you sort of a progression of our models. So when we started, our nets were very simple, and we had really very sort of primitive simulations of them. And then we graduated to more sophisticated models. Our nets got bigger. Our model of the net got more sophisticated, more accurate. Then we included in our simulations a debris. Here, the debris is just a box, a very sort of simple piece of debris. But this is a very big step when developing a simulation, because now we have to model the contact, all the contact dynamics between the net and the debris. And then we progressed further with this. We made our debris look more realistic. This is actually modeled after one of the upper stages. We made the debris rotate. And at this point, we had some interesting insights from our simulations. So initially, we sort of thought, well, the net is going to go around the debris and it's just kind of going to sort of stay containing the debris. But as you will see in this video, after a while, the net opens up and flies away from the debris. So needless to say, that wasn't going to be a very successful capture mission. And so finally, here's another movie illustrating the progression of our modeling and simulation tools. So now we include the chaser, which is this little box up at the top, and then there's a tether, right? This is a tethered net. And then we also included a closing mechanism to ensure that the net stays around the debris. All right, so I'll now sort of switch gears a little bit, and I'll talk a little bit about the multiple space debris removal work and mission that we researched. So the motivation for this was the fact that, as I mentioned earlier, there's a general consensus that removing 5 or more large debris per year would stabilize the debris environment in LEO. And so we embarked on this work with the objective to investigate the feasibility and optimization of a multiple space debris removal mission. And so really, we wanted to develop some tools that would allow us to figure out, is this actually feasible? Can we remove 5 large debris in a year? How expensive would it be in terms of fuel requirements? And so we developed a time optimal control formulation for doing a recursive removal mission scenario. And so let me explain to you what I mean by this. So this is a figure showing, Earth at the center in blue. Then we have an orbit in green from which our chaser, which is a blue diamond, would sort of start. And then in this figure, I have 3 debris, each in their own orbit. And the idea for a recursive removal mission is that the chaser would travel to debris 1, capture it in whichever way, robotically or using tethered nets or using something else, and then bring it down back to a very low orbit, release it. From that orbit, the debris would deorbit naturally very quickly. And then the chaser would move to the second debris, right, to the second debris orbit, capture that, bring it down, release it, and move then to the third debris orbit. And so this is sort of a recursive mission where the chaser goes to one debris, brings it down, back up, and down. Now, so we wanted to look at optimizing this mission from the perspective of minimizing the time that it would take, but of course, the fuel requirements for a mission like this is also a big concern. So in formulating this problem, we early on realized that we needed to look at a chaser that would have low continuous thrust capabilities, so thrusters that would produce not a lot of thrust, but continuously. And we also realized that RAN differences between orbits, and I'll define RAN in a second, make the mission quite expensive. It requires a lot of fuel to do orbital transfers between orbits which have very large RAN differences. Now, what is RAN? RAN stands for right ascension of the ascending node. That's basically an angle between, it's an angle measured in the equatorial plane between the vernal equinox and the intersection between the orbit and the equatorial plane. So the important thing here is that the drift orbit would allow the chaser to reduce the RAN difference by while the chaser would be drifting for some time in the drift orbit under natural RAN drift. All right, so what are some of the special considerations for such a mission? Well, one of them is debris selection. How do you select the debris that you're going to go after? And the things that you want to consider here are the risk factors of the debris and their orbit, because that ultimately impacts the cost of the mission. Once you've selected your debris, then there's a question of how are you going to sequence, in which order you're going to remove the debris. And again, the considerations here are the cost of the transfers between the different orbits, achievable RAN changes, and how much that would cost in fuel. And so we developed a methodology to solve the time optimal control problem. And then we applied this methodology to sort of different sets of debris. And I wanted to show you an example here of a set of 5 debris, which included Daiichi. Daiichi was a Japanese spacecraft, Envisat, that I already talked about, and then 3 sort of upper stages as well. And if you look at the last column, which shows the mass, you can see that these are pretty massive objects, 4,000 kilograms, 8,000, 9,000, etc. And also this table presents the orbit. So the standard orbital parameters that are of concern here are the semi-major axis, A in kilometers. That's basically the radius of the circular orbit. And then we have the inclination in the second column, I in degrees, and then the RAN. And you can see that there are substantial RAN differences between some of the debris in this particular set. And so the outcome of the solution is basically a detailed mission plan as summarized in this table. I'm not going to go through all these numbers, obviously, but basically the mission plan would tell us, okay, you're going to move to a drift orbit located at this semi-major axis. Then you're going to travel to the first debris. And as part of the solution, you get all the detailed information, how much time different parts of the mission would take, how much fuel you're going to need, how long you're going to spend in different drift orbits. So the important columns here are actually the last 2 columns, which show the time spent in different parts of the mission and the fuel cost. And at the bottom, we can see that the mission total for this particular set of debris was about 814 days, which is actually more than 2 years. And the fuel cost was about 2,800 kilograms, which is also quite substantial. But this is just to illustrate, what kind of information we can get from this time optimal control solution. All right, maybe I'll take a few minutes if there are any questions before I continue.
Quite a few, so maybe I'll just pick a couple and then we can do more. One really good one we had was related to concerns about how expensive it is to get mass into orbit in the first place, and wondering if there's any way to recycle objects that are, debris, rather than just deorbiting and destroying them.
Right. Okay. So it is expensive, and that's actually one of the points I was going to make right here. Active debris removal is very costly. You're launching a spacecraft to get the debris, and then and you're basically going to, it's a kamikaze mission, right? Both the spacecraft, the chaser, and the debris are just come crashing to Earth. There is a lot of work, or quite a bit of work that's happening right now on what's called on-orbit servicing. And this is an area that's a little bit complementary to space debris removal because some of the problems are very similar. So the idea behind on-orbit servicing is that, okay, you have a defunct spacecraft. Very often the spacecraft becomes defunct because it simply ran out of fuel to do the orbit maintenance. And so why not, refuel these spacecraft? So that's one possibility. Sometimes we send a spacecraft and something malfunctions very early on in the mission. And sometimes it's actually very simple malfunction that could be easily repairable if you sent another spacecraft. Then there are people that are very much looking at recycling ideas. So if we have this defunct spacecraft and this other piece of defunct spacecraft, can we kind of recycle these things and put another spacecraft from these pieces in orbit? So there are people working on these. There are various concepts. We are still quite a ways from, sort of having these concepts become a reality, but it's definitely something that people are working on.
That's great to hear. I think we had another question. For your net mechanism that you were talking about, someone wanted to know, how does it close? How does that closing mechanism work?
Right. So here again, there's sort of several ideas that people have proposed. We came up with an idea which resembles a little bit, if you have a sleeping bag and you pack it into like a little sack and you just kind of pull on the string to close it up. So the idea that we had was, why not take our main tether and sort of extend it out along the perimeter of the net. And then once the net is sort of around the debris, we were going to pull on the tether to close it. So that was one of the ideas that we worked on it, and we tested it in simulation, and it worked pretty well. So, but there are also other concepts for closing the net.
Cool. Maybe we can just do one more short one. I think one person wanted to know, there was a previous slide where you mentioned that maybe like 5 big space debris removals per year would be sufficient for, I guess, stabilizing low Earth orbit. They were wondering how many years total would be needed for that, like 5 per year for how many years?
So the idea here is that, based on the prediction tools that we have at our disposal for sort of predicting the debris environment and the evolution of the debris environment, the 5 to 10 debris per year number is agreed on as something that will stabilize the environment. In other words, it will stabilize the growth of the debris. So there won't be, the number of debris will not grow, but will kind of more or less stay constant and maybe even decrease a little bit. So it's something that we would need to continue doing, I guess, ad infinitum, for as long as and of course, these numbers are based on predictions of how many things we're going to be launching into space. But for now, over I'd say the foreseeable 10, 20, 30 years, that's kind of the number that people have in mind. Yeah.
Like a continued maintenance sort of.
Yes, exactly. Yeah.
Awesome. Well, I think that's probably enough questions for now. So
okay.
Welcome to continue.
Okay, so this brings me sort of to the next topic, which is passive debris removal. And as we were just saying, active debris removal is expensive. And so researchers have been looking into other ways to speed up really the deorbitation of debris, because that's what this is really about. And one strategy that received quite a bit of interest utilizes the effect created by coupling between two orbital perturbations. And this is called SRPG2 coupling and resonance. SRP here stands for solar radiation pressure, and this is one of the perturbations, one of the forces and torques that's exerted on objects in space. And J2 represents the gravitational effect due to the fact that Earth is not spherical. Earth is not a perfect sphere. It's kind of a squished spheroid. So these two perturbations, when they couple, may create what's called a resonant effect. And this phenomenon has actually been known, and theory for a long time. And theory for this was put forward back in 1933. But what happens when you have these two perturbations couple is that this can lead to a significant increase in orbit eccentricity. Now, so what does that mean? Well, so I have a little figure here. You have Earth, then you have orbit, and then you have perigee, which is the closest point in the orbit to Earth. And increasing eccentricity means that as the orbit becomes less circular, so it becomes more elliptical, as this happens, the perigee, which is the closest point in orbit, gets closer and closer to Earth. So by increasing eccentricity, you end up lowering the perigee to an altitude where the atmospheric drag becomes significant enough that you can then accelerate the time to deorbit. So that's sort of the basic idea for this phenomenon. So there's been quite a bit of interest in this over the last several years, and there was a Redshift project, which was a European consortium of researchers, and as part of this project, so first of all, this project was motivated by basically the need to minimize environmental impact of mega constellations, given that that's what's happening over the next decade. And essentially, researchers under this project created literally a cartography of resonant orbits in LEO. Now, the thing about this SRPJ2 resonance is that it only happens in very few and specific orbits. So, for example, so this is an example of a resonant orbit. It has a semi-major axis of about 8,000 kilometers. It has a particular inclination of 39.5 degrees and initial eccentricity of 0.03. So when we started looking at this, one of the first things that we actually wanted to do is validate, this effect in simulation. And so I have a graph here that shows the eccentricity as a function of time, and this was done over 10 years. And this is a result from an orbital propagator that we developed, which I'll talk about a little bit later again. And these curves were obtained by varying the inclination slightly away from the resonant orbit. So the resonant orbit is at 39.5, and we tested this for inclinations ranging from 38.5 to 40.5. So fairly small deviations in inclination. And so what you can see here is that the yellow line, which corresponds exactly to the resonant orbit, you can see that the eccentricity is increasing, right? And it's just increasing over the 10-year time frame. While for the orbits that are near the resonant orbit, you don't see this phenomenon. So indeed, this is a real, or this is a phenomenon that we can definitely reproduce in simulation. And so again, as the eccentricity increases, you bring the perigee closer to Earth until you get into enough atmosphere to slow down the debris and to bring it deorbited naturally. All right, so in my group, we've undertaken to look for the SRPJ2 coupling or resonance among all objects for which observations are available. And this is actually work that's ongoing. One of my PhD students, Catherine Massey, is working on this. So I wanted to illustrate this with an example of a spacecraft. This is a spacecraft called Echo 1. It was a NASA spacecraft that lived in 1960s it was in orbit for about 6-7 years. And this is one of the spacecraft for which the SRPJ2 coupling is actually very prominent because of the high area to mass ratio. The spacecraft was actually a balloon, so it had a very large area, but was fairly light. So what I'm showing in the figure here that I've just put up, first of all, there's two plots. The top is the semi-major axis over time, and the bottom one is the eccentricity. And in each figure, I have sort of three curves. The black is the observations. And the observations for things in orbit come from TLEs. These are two-line elements which give us all the orbital elements of an orbit. So the black dots are basically measurements. And then the blue and the orange are what we compute with our simulations, with our orbital propagators. And the orange one is without the SRP perturbation in the orbital propagator, and the blue one is including the SRP perturbation. So therefore, the SRPG2 coupling is in effect. And so you can see that the eccentricity definitely increased quite a bit. So it sort of oscillates, which is one of the reasons people call this a resonance. And because of this SRPG2 coupling, the spacecraft came down to Earth much faster than if this coupling didn't exist, right? So remember, the orange line shows no SRP, while the blue line shows SRP included. And you can see that it descended to Earth quite a bit faster. So we're actually we are reviewing databases and TLEs for about 50,000 objects in space with a view to finding this phenomenon in real objects in space. Another part of our work on the passive debris removal has had to do with the idea of looking for another type of resonance. And we've called this the SRPJ25 resonance. And this is essentially a new type of resonance that also leads to substantial increase in eccentricity. And the way it works is by imposing a particular spin state on plate-like spacecraft. So remember, one of the things I mentioned for the SRPG2 resonance, this happens in very few specific orbits. Now, your debris might not be necessarily in a resonant orbit, but by making the debris spin, giving it a particular spin state, we can induce this new SRPG25 resonance. Now, you might think, well, okay, you're proposing this for plate-like spacecraft. Are there plate-like spacecraft? Well, as a matter of fact, if you look at Starlink, which is a spacecraft from SpaceX, that's part of the SpaceX's mega constellation, most of the spacecraft is actually the solar array, and that's a flat plate, and it's only a small part of the spacecraft that's the body. So again, to sort of give you an illustration of this, here I'm showing propagation results for plate-like debris modeled after the solar panel of Starlink. We've put it in sort of a realistic orbit. And again, I'm showing here the semi-major axis as a function of time and the eccentricity, comparing spinning in blue and not spinning. And you can see that the SRPJ25 resonance is in effect. The eccentricity does increase, and we are able to deorbit, bring to Earth the spinning spacecraft quite a bit faster than had it been not spinning. All right, so this brings me to sort of the last topic that I wanted to cover today, and that falls under the subheading of science. So we talked about the issues arising from the rotational motion of debris, right? We said that while debris tend to tumble in space, and if you want to do active debris removal, then you're going to have to grab something that tumbles. And if you want to do this with a robotic arm, well, that's not so easy. So if we are going to be planning ADR missions, then we thought that it was important to have models and simulation tools that would allow us to predict rotational motion of debris for many years, right? Because if you're planning an ADR mission for, I don't know, 2028, you want to know how is your object going to be tumbling when you send that mission, right? So that you can be properly prepared to accommodate this. So, so we initially, when we started looking at this, we were very much motivated by the ADR application. But then as we sort of did more research and looked at the literature on the subject, we actually discovered some fascinating facts and mysteries. And this work ended up sort of taking a life of its own. And in particular, we became very interested in accurate modeling rotational motion over long term, so over decades. And we wanted to compare our models to observations. And another thing that we were interested in, we wanted to have a clear idea of how the rotational motion affects the orbital motion. And this is important for orbital predictions and re-entry analysis. So what are these mysteries and sort of fascinating facts that I mentioned earlier that we came across? Well, one of the mysteries was actually the Envisat spacecraft. And this is why the title of the slide is the Underset Enigma. So one of the things that we found out was people observed, or researchers observed, a substantial spin-up of Envisat that happened shortly after it was declared defunct. So what I'm showing here is the plot of the angular velocity of Envisat over time. This vertical dashed line is the time when ESA said, okay, the spacecraft is defunct. And the little crosses here are observations that were collected of the rotational motion of Envisat. And you can see that shortly before it became defunct, it was rotating fairly slowly. And then you see this increase, right? The little pluses are going up to about 3 degrees per second. And to this date, nobody actually knows what caused this the spin up. After the spacecraft became defunct, many observatories around the world sort of got in and started taking observations of the rotational motion, and it shows that the spacecraft is slowing down. And as you can see, there's actually quite a bit of agreement between the different observational campaigns. So there's several observational campaigns here from different groups, and there is in general an agreement. So that was good. But the other part of the enigma was that even though there was quite a bit of agreement on the rotational speed of Envisat, there was actually a lot of disagreement and sometimes even contradictions on the orientation and the motion of the spin axis of Envisat. So I wanted to show you this graphic here that I have at the bottom right. So first of all, this is not to any particular scale. This is really just to illustrate things. So I have Earth in blue. Then I have the orbital plane of Envisat. All right, so the orbit is sort of this, the circumference of this reddish graphic. And at the bottom, I have the little schematic of the spacecraft itself, right? This is Envisat itself. And then what I've shown here is the angular velocity vector, omega. This is the axis of rotation of Envisat. And so what we found was that there was actually quite a bit of disagreement on how that axis of rotation is oriented and how that axis of rotation moves with time. So to give you some examples of the conclusions drawn from different observation campaigns, some people were saying that, well, the axis of rotation is oriented 28 degrees from the orbit normal, from the normal to the orbit, and it mutates with the orbital period. Then some observational campaigns were saying, well, no, actually we think the axis of rotation is fixed, and it's fixed at 17 degrees from orbital normal. And then other observational campaigns were finding very large spread in spin axis. So we were really pretty sort of fascinated by all of this, and that motivated us to work on developing models and looking very closely at the rotational motion of space debris. So in this work, which was a big part of the PhD student Luke's second year, we developed a comprehensive model of the rotational motion and an orbit attitude propagator, Dispose, called Dispose. We validated Dispose against observations of rotational motion, and we employed Dispose to investigate the rotational motion of Envisat specifically, as well as some other spacecraft. And we were trying to shed some light on what Envisat's rotational axis was actually doing. So I'll say a couple of words about Dispose itself. It's a state-of-the-art orbital attitude propagator. And it includes a number of perturbations that are not commonly modeled. And they are the gravity gradient torque, the aerodynamic torque, the eddy current torque, the radiation torques, which come from direct solar radiation. This is the SRP that I was talking about earlier. Then you have the albedo effect, and then you have the infrared radiation from Earth. It also includes internal energy dissipation and hypervelocity impacts. So these are all effects that are perturbing the rotational motion of the debris from what we would normally call a torque-free motion. So all of these effects are modeled and disposed to probably the highest degree of accuracy available. So in this slide, I wanted to show you some of our validation work. So you have this powerful modeling tool. We're able to simulate the rotational motion of debris over long periods of time. We wanted to see if we can validate it against some of the observations. And to do that, we used spherical geodetic satellites, for which there was a lot of observational data available. And one of the reasons for it is because these satellites are equipped with retroreflectors. And so it was very easy to observe their rotational, it's fairly easy to observe their rotational motion. So what I have shown here are three sort of figures. The first one on the left is showing the period, which is inversely related to the spin rate. And then the other two figures show the declination and the right ascension. So this basically gives you the orientation of the axis of rotation, right? So it gives you information on how the axis of rotation is oriented in inertial space. And in each figure, we have the black line, which is simulation with Dispose. So this is the results from our simulations. And then we have two observations. We have, so these are from two sort of sources of observations. We have the light curves in orange dots and the SLR, which is the this is a laser ranging system in blue. And what you can see is that there is actually pretty good agreement between our simulation in black and the observational data. So that gave us a lot of confidence in our models and in our simulation tool. And with that information, we then were able to really investigate the rotational motion in Envisat. And so at this point, we hypothesize that Envisat's rotational motion has three distinct motions. And I say that we're hypothesizing on this because until we have enough observations to confirm this hypothesis, it remains a hypothesis. So basically, we think there are three distinct motions that contribute to rotational motion of Envisat. The first one is the precession of the angular momentum with the orbital plane. So remember, I introduced to you the angular velocity vector, which is shown here kind of in this dark pink. Any rotating body also has an angular momentum, which is called h, and it's shown here in sort of this bluish, purplish color. So as the orbit precesses, so the orbital plane rotates about the Earth's rotational axis, the angular momentum is precessing as well. So that's the first contributor to the rotational motion. Then we have the nutation and libration of the angular momentum around the orbital normal. So that's illustrated by these two cones. So basically, the angular momentum vector is nutating about the normal to the orbit. So the orbit normal is shown here in this red vector n. And essentially, the angular momentum is doing sort of traveling along a cone around that orbit. That's called nutation. But in addition, that cone itself is sort of librating. And the limits of the librational motion are shown by the blue cone and the yellow cone. And the third part of the motion of the angular velocity vector is the angular velocity vector is actually wobbling around the angular momentum. So omega, this pink, dark pink vector, is itself sort of wobbling around h. And remember that the spacecraft itself is rotating about omega, right? So these are these are contributions, the main contributions to the angular velocity, to the motion of the angular velocity vector. And that's sort of our current understanding of the rotational motion of Envisat. All right, so with that, I'm going to conclude my talk. So as far as space debris goes, I think this will likely become a bigger problem in the coming decade because of the launch of mega constellations. I think that active debris removal is actually reaching a pretty high technology readiness level. We've had some successful demonstration missions, but nevertheless, it's an expensive mission. And at this point, I'm not really sure when a real mission will take place. So there's really no certainty on when that might happen. The passive strategies that I talked a little bit about by exploiting this sort of SRPG2 resonance and possibly the new resonance that we proposed. At this point, I'd say the word is still out on whether this is going to be at all a practical solution, and this requires more work. And the last thing that I want to mention is that rotational motion of large space debris is complex. I think it's fascinating. Researchers are still working on understanding it, modeling it, and modeling how it affects the orbital motion. And I think that brings me to the end.
The Envisat rotational motion is just, I can't even hold all of that and visualize it. So props to you guys for trying to figure out all those components. So I think we have many more questions, and I'm just going to try and pick a couple to start with, and we can go from there. So someone had a question about, for this passive removal, the like resonances you talked about. Is there like a particular like rotation rate or like range of rotations that you need to achieve that resonance?
Yeah. So yes, so there would be a particular rate. It would depend on the orbit that the object is in, and we're finding that it's a very slow rate, and essentially it has to do with you sort of are trying to maximize the SRP effect, the solar radiation pressure effect, and so you want to be sort of pointing your plate-like spacecraft as much towards the sun. So it's a very slow rate, and you need to do some work. You need to have some mechanism to get your debris to maintain that rotational motion. This is why I'm saying it's not at all clear whether this is going to be a practical solution. So yes, so definitely we know how to compute that rate.
Great. Another question, someone wanted to know, actually a couple people were wondering, sort of like what are the main methods we use for detecting debris in the first place? I think you mentioned like observations from observatories.
Yeah, so our main method is we can observe anything that's larger than 10 centimeters, we're tracking from the ground. So that's happening continuously, right? And that information gets published every few hours. TLEs, the tune line elements, which is basically information on the location of the debris in orbit, gets updated. So that's what we do. For things that are smaller than 10 centimeters, we're out of luck. And this is one of the reasons this is sort of an issue, because as I've mentioned, even something as small as, an object that's about 1 centimeter in size can create substantial damage. So we observe debris from Earth, and that information, of course, is available to satellite operators.
Are there like just particular telescopes that are sort of constantly monitoring, or is it sort of like on and off thing?
I don't think I can tell you exactly, because I'm not sort of so much, I'm not really that involved on the side of things.
Mhm.
For us, we get these TLEs and we're happy. Yeah, I don't know if Catherine is on the call. Maybe she'd be able to answer this question.
I'll keep an eye on the chat and see if we get another response. I was just curious because I'm on the astronomy side, so I'm like,
Yeah.
Very cool.
Yeah. So there is what is it called? The Space Surveillance Network. There's a couple of large networks. One is the U.S. based, and the other one is Europe based, and that's where these observations are sort of actually happening, and information gets published.
Very cool. I think we also had a really good question. Oh, yes. So I guess this is sort of maybe like a comment/question, but someone mentioned that basically shouldn't space agencies impose requirements on space programs to like build in a deorbiting feature rather than having to go back later and fix it? So is this something that's being discussed?
Absolutely. So this is actually happening. There are guidelines that exist, international guidelines that exist, that speculate that all things that we launch into space must come down to Earth within 25 years. The issue is that they're guidelines, so they're not laws, they're not necessarily enforceable. Some countries, I can't remember now, I think France might be one of them, actually have made it a legal requirement. But for as long as they remain guidelines, it's that are not enforceable, it's not necessarily something that happens. Because ultimately, people that launch spacecraft, for example, if you launch a communications spacecraft, you want to get as much life out of it as possible. To meet these guidelines would require you to have some fuel remaining to get your spacecraft back down, so that you can meet this 25-year limitation. And an operator that's operating communication satellite that's wanting it to be functional for as long as possible is not necessarily wanting to, cut the mission life short, have enough fuel to meet this guideline. So that's sort of the current status, to the best of my knowledge.
Tricky.
Yeah. Yeah. There's politics involved in this as well. Yeah.
Let's see, other questions. I think we just had a question from Susan. Who's paying for these missions? And I feel like this might also have some politics in it as well for the debris capture.
Yeah, so that's another question. And again, there's sort of discussion on this. So for example, with Envisat, it was an ESA launched spacecraft. And so they're the most concerned about it. And one can make an argument, well, whoever launched the spacecraft, they should be responsible for a mission to remove it. To to date, we haven't had a real mission, right? We haven't had a real mission. The demonstration missions are funded by, for the most part, government funding, to the best of my knowledge. So I mentioned two of them: Remove Debris, which was a mission from the University of Surrey. I'm pretty sure that well, in fact, I know that they've gotten funding through Horizon 2020, which is a European funding umbrella. And Astroscale's mission, I imagine, is funded from whoever is funding the startup. So, so the purpose of the demonstration missions is to demonstrate that, look, we think we have the technology to do this, or maybe not, and some more technology needs to be developed. And of course, a company like Astroscale, which is a startup company, they're hoping that eventually, if they demonstrate that they have the technology to do this, then somebody will give them the money to do the real debris removal mission. But who that somebody will be, I guess, will depend on which debris is moved.
Which country does it belong to? Yeah.
Exactly. Yeah.
And I guess one more sort of tricky politics-based question. Someone was wondering about, so I guess satellites can have sort of relations to the military, and has debris capture have you guys been thinking at all about like a scenario where you have someone that destroys satellites on purpose as like a military act, and how to deal with that, I guess?
Well, so in fact, China did this in 2007, right? They conducted an anti-missile test, and they destroyed one of their defunct spacecraft, and that created a lot of debris. And again, I don't sort of know what is the current legal framework for acts like this. So yeah, I don't really think I can say much more than that.
Might be another tricky scenario.
Yeah.
Let's see. I feel like maybe we have time for maybe a couple more questions. Let's see. Oh, okay. We just had a question in the chat from someone asking about, I guess, like, what are the sort of overarching guidelines or laws on, I guess, maybe like space-related debris capture?
So I'm not aware of any laws on the debris capture itself. Yeah, I'm not aware of any laws on debris capture at this point.
Okay.
But again, there are, definitely there are people involved in space law, and debris related issues would be a subset of that area. We have some good people working on these in these areas at McGill.
Oh, cool.
But I'm really not the best person to give you answers on this.
Yeah, maybe someone in space. I didn't even really know there was a space law.
Oh yeah, very much so. Very much so. Yeah.
Okay, and I think maybe we have a fun question. Someone wanted to know, is space debris big enough to see? And I guess so that would mean like with your eye, maybe like from Earth, or.
I don't think so. I mean, an object that's very large. So the larger objects, right, like objects that I mentioned, Envisat is probably one of the larger pieces that's out there. I don't think it's visible from Earth with a naked eye. I'm pretty sure it's not.
Yeah.
Space station, which is very large, and it's in a substantially lower orbit. It's somewhere around 300 kilometers. I believe that you can see it sometimes. You sort of see a dot in the sky, but it's just gonna look like a dot to the naked eye.
That's awesome. I think you can see like iridium satellites, maybe. I don't know. I feel like I've seen something about that. There's certain satellites that are very reflective, but not like the debris, just like actual satellites.
Right. Okay. Maybe.
I guess I think we've gotten to most of our questions, so that looks pretty good. I had one that I can ask that I thought of while you were talking. I was curious what happens if a capture fails or like messes up. Do you have a way to like retry, or is there a risk of like a cascade or something worse happening?
Well, so that's another thing that people are thinking about as they're looking at these debris removal technologies. So, imagine you're trying to capture using a robotic arm. So if you miss, can you try again? Well, possibly if you don't, as long as you don't hit something and damage the arm, you could kind of maybe back up a little. So definitely there are some options. With a tethered net scenario, you can have a backup option where you carry more than one tethered net. So you've launched one, you missed. Well, you launch another one. The good thing about tethered nets is that they're very light, so you can easily carry spares. So yeah, I think it would depend very much on the exact technology that you're using to do the capture.
I see. I like the net. The net idea sounds good. Well, yeah, I feel like we've already taken up quite a bit of your time. So thank you so much for answering all these questions. And yeah, just learned a ton. And we've had a lot of comments in the chat saying thank you. So really, really great topic.
Thanks everybody for joining, and I hope you enjoyed the talk.
Yeah, thank you so much. And I guess just before we end, I'll say we're doing one more lecture next week as part of McGill's Space Week, which is also aerospace themed. And so if you're interested, please go to any of our social media pages just to find out more about that. It'll be on May 5th at 7 p.m. So with that, good night.
Bye-bye.